So, the lectures of propagation of waves we have now come to describe the propagation of electromagnetic waves in an external field. So, as a consequence of having an external field, the background loses its sum of the symmetries, and due to this the propagation may be propagating with a different speed or velocity in different directions. This thing can happen in a situation when the underlying space is empty or vacuum, and in a situation where the underlying space is filled up with some material medium. In the case of vacuum, the number of degrees of freedom of the electromagnetic perturbations do not undergo any change. The reason is the following: the polarization tensor in an external magnetic or electric field or photon self energy though it depends on the field strength tensor in a particular direction, but as the momentum of the photon tends to 0, the size of the contribution that comes from this particular object also tends to 0. So, the usual definition that provides a clue to the mass, that is, the energy should be 0 and the spatial component of the momentum should also vanish, and then if the contribution of the self energy is still finite, we should think that it has acquired a mass, does not hold good anymore. So, in an external field, the number of degrees of freedom of the photon is identical to the same as in vacuum. The sector from where the changes creep into this system is the presence of the medium. It's a medium effect that introduces some amount of mass for few modes of the photon. So, a 4 component object that we define here by A mu, the gauge field, should in principle have number of components as there are the number of values available for the index mu to take. So, in general, this gauge field should be expanded in terms of a basis vectors, rather 4 basis vectors, out of which the 3 objects that appears should correspond to physical modes, and the one that is left out is sacrificed for the gauge freedom. To make things clear, the last line in this slide actually shows you the decomposition of the gauge field in terms of the form factors and the basis vectors in terms of which it is they are expanded. The basis vectors that we have chosen for our purpose using the variables those describe the system are given or given in terms of some symbols like B1 alpha, I alpha, U tilde alpha and K alpha. Their corresponding form factors are A parallel, A perpendicular, A longitudinal and A gauge fixing. Before I go on to describe their form, little bit of physical insight about their construction may not be out of place. So, if we look at the definition of B1, it is the momentum vector k mu is contracted with the field strength tensor That is how we get. So, only for those values of the field strength tensors, those are non-zero, the components of the first vector B 1 are considered to be, or you do not have to consider it, by definition they are non-zero. And for the directions or for the components for which these field strength tensors are non-existent, for those components B 1 vectors are also non-existent. So, in a situation where only 1-2 component of the F is non-zero, we should have B 1 and B 2 to be the only ones of B hat 1 to be non-zero. So, that is one of the reason behind the choice of the parallel symbol for A in the form factor that is associated with B 1 of alpha. Similarly, if we go to talk about A perpendicular, then this vector I alpha, that is the associated vector, it has non-zero components in those direction, in rather where B 1 had no contribution. That is, this is orthogonal to I alpha is orthogonal to B 1, and that is the reason why you have put a perpendicular sign on the corresponding form factor A. The longitudinal direction in 3 degree of freedom could have been taken to be the direction of the photon's 4 momentum, but we are not exactly working on 3 dimension, we are dealing with 4 dimension, and 4 dimensional space. The vector that can give a direction which is orthogonal to B 1 I and k is u tilde, and that is given by the second line left side of the current transparency, that is this one. We can check that if we contract it with 4 momentum k mu, then it vanishes. If it is contracted with I, it again vanishes. It vanishes when it is contracted with B 1, but it does not when it is contracted with the vector B 2. Had we been working in vacuum, then This 2 would have been sufficient to describe the system, because there was no medium and there was no necessity to build up a vector using the medium for velocity. And the moment there is a medium for velocity that enters into this game, that freedom that B 2 is orthogonal to something that is constructed out of the medium for velocity is lost. So, we had to invent this particular vector that we have defined by I. So, the 4 vectors, this B 1, I and U and K altogether forms a basis in which A was designed to be expressed, or we expressed A in terms of these 4 vectors, and out of the 4 scalars, those are seen here, capital A parallel, capital A perpendicular, capital A longitudinal and A G F. We can set A G F to be equal to 0 and deal with the system's 3 form factors, a parallel, a perpendicular and a longitudinal. The objects those are sitting here N 1 or N L or N 2, they are essentially normalization constants to take the dimension away from these objects. So, the dimension of the vector gauge potential and the dimension of these form factors remain the same with this choice. And K perpendicular that might have appeared in places or K stand for the 2 transverse components of the spatial K vector that is orthogonal to the z direction, and K mod of K, capital K, actually corresponds to the square root of the individual squares of the momentum vectors 1, 2 and third direction. Now, as we discussed and we are trying to motivate that the system is over determined, that means the number of variables that the system has is more than the physical degrees of freedom. So, it was necessary to perform a gauge fixing, and the gauge fixing was done by setting this A G F to be equal to 0. And once this is set to be equal to 0, The Lorentz gauge condition that says that the 4 momentum and the gauge field are orthogonal to each other is maintained by construction. So, we are on a safer ground. There is one thing that you should remember here, that is this set of vectors that we have taken as B 1, I and k and u tilde, this 4 system, they are orthogonal to each other of course, but the issue is they will also be orthogonal to each other if we rotate the frame by some angle in 4 dimension. So, as long as we do that, maintaining the orthogonality of these vectors, then the analysis will turn out to be invariant and the conclusions drawn from any orientation or configuration of these vectors will be as good as the same for the others. So, with this let us move to the other interesting observations that may come on our way. So, one among them was to note that we can have a effective metric description in this particular space, which is given in equation 20. There was a condition of gauge fixing that we have already discussed, and the particular variable that acts as a constraint, and how do we relate each component of a mu, 0th or the spatial components with in the new coordinate system can be done by suitably contracting the gauge potential and projecting out the particular direction that we are interested in. All right. And we also have already discussed about the discrete symmetries of these form factors, parallel, perpendicular and longitudinal, and the expectation that we have is in any equation if they appear, then in each term that the equation may have, these property, that is their CPT property, should be the same. So, with this, if we analyze the equations of motion in an external magnetic field, then for the 3 degrees of freedom that we have at our disposal, we have 3 equations, perfect, out of which you can, as can be seen, the last one, that is at the third in the set of 3 equations, does not actually talk to anybody or interact with anything. So, it is a Fourier space description of the longitudinal degrees of freedom. Pi L is the longitudinal form factor for the photon self energy. However, the other two, degrees of freedom, that is a perpendicular and a parallel, are not independent of each other, at least as long as this object pi p is non-zero. If the object pi p is 0, then there is no problem. All the three components of the gauge potentials form factors, all of them are independent of each other. But as long as pi p is non-zero and finite, one starts getting mixed with the other and vice versa. In situations where there are more degrees of freedom that interacts with the photon can be tractable by similar set of equations where their individual excitations can be seen to couple with the other modes of excitations, either the perpendicular or the parallel or the longitudinal, but when they are not there, these three are sufficient. The second point here that is worth remembering, that is, in general, this coupling or this interaction depends on their discrete transformation properties, that is, these extra degrees of freedom that we are talking about. You can have a situation where the extra degree of freedom that we have just mentioned is a scalar quantity, and we have similar situation when this extra degree of freedom might be a pseudo-scalar quantity. We can give mass to each one of them, non-zero finite mass, and we can expect that the longitudinal direction of or longitudinal form factor A L, because it is the 0th component of the spin 1 vector potential, it should have coupling to both the scalar and the pseudo-scalar, but it does not happen so. The longitudinal excitation or mode of excitation gets triggered only when there are pseudo-scalars, those are interacting with the photons. Thank you.